The goal in this video is to extend our basic principles, and in this case we'll extend it to Newton's second law and apply to a control volume. Newton's second law, sometimes we may also refer to that as the linear momentum equation. And if you recall the Newton's second law for a control mass, so we'll start with a control mass, look at Newton's second law, and then use the Reynolds transport theorem to obtain Newton's second law for a control volume, right? Just like we did for conservation of mass, COM, we wrote down the conservation of mass for a control mass, and then we used Reynolds transport theorem and extended it to a control volume. Same kind of procedure here. So if you look at the Newton's second law for a control mass, this is given by equation 1, right? What is equation 1 telling us? On the left-hand side is the rate of change of momentum. On the right-hand side is sum of all the forces, right? So it's the same as F equals ma. It's expressed instead of ma, we think of it as rate of change of momentum. And F, instead of appearing on the left-hand side in F equals ma, we got F on the right-hand side in this expression, right? So let's focus over here. Rho dV is the mass of a little differential volume, dB. And so that's going to be dm, if you will, and then multiplied by that by the velocity of the fluid in that region, measured with respect to an inertial reference frame. That gives me the momentum, and then I integrate this momentum over the entire control volume. That gives me the total momentum of the fluid sitting inside my control volume, and then I'm trying to find its rate of change on the left-hand side, right? On the right-hand side is the sum of two forces. The first force is the surface force, so that's a surface integral, and the double prime indicates it's a surface force per unit area. The second term is a body force, and the triple prime here indicates this has units of force per unit volume multiplied by the volume. The second one is a volume integral, the first one is a surface integral. And as you know, Newton's second law has to be applied with respect to an inertial reference frame. So this velocity v sub inertial is the velocity as seen with a, let's say, a stationary reference frame that one might use in a problem. If you apply Reynolds transport theorem, right, so this is the time derivative of some quantity inside a control mass. I want to convert that to the time derivative of the same quantity, if you will, but now extend it to a control volume, right? So in order to do this, we apply Reynolds transport theorem, right? So if you recall Reynolds transport theorem, so this is the time rate of change of the B stuff in my control mass. This is the time rate of change of B stuff in my control volume, plus the net outflow minus inflow of the B across the control surface, right? So this is a surface integral. Again, that's a volume integral. So this is Reynolds transport theorem. Again, it's just a bookkeeping statement. It's not a basic principle or a physical law. Okay, of course, the generic quantity B is what is being transported over here. And so this little b in this present case would be V inertial, right? And V inertial, this is a vector quantity with the arrow on top. So all I need to do is on the left-hand side, apply the Reynolds transport theorem and replace the left-hand side by this expression, okay? So that's what I did, right? So as a rate of change of momentum for the control mass equals that for a control volume plus the stuff that goes out minus in of momentum across the control surface, right? So up to this point, we've only invoked Reynolds transport theorem, which again, I said, is not a basic principle. When I want to invoke Newton's second law, that means I need to equate the rate of change of momentum to sum of all the forces. So that's what I'm going to do next. So invoking Newton's second law through equation 1, we get the Newton's second law for a control volume, and which I will copy over on the next slide, right? Again, let's interpret these terms. This is the rate of change of momentum of the fluid sitting inside my control volume. Remember, rho dV is the mass. Multiply that by velocity, measured with respect to my inertial reference frame for that fluid, and that gives me the momentum. Then I integrate that over the entire control volume, and then I take the time rate of change of that quantity, right? So that's the rate of change of momentum. Same idea over here, right? So rho times VL dot dA gives me the mass that goes in and out of the control volume, and then I need to multiply that by the velocity of the fluid measured with respect to my inertial reference frame, and that gives me the outflow rate of momentum minus inflow rate of momentum, right? It depends on the sign of the dot product where you have outflow or inflow. On the right hand side is the sum of the forces acting on the control volume. One is a surface integral, the other one is a volume integral. So if I extend this, or if this is sort of written in vector form, if I want to apply it to, say, the Newton's second law along the x direction in a Cartesian coordinate system, all I need to do is wherever v inertial appears, I take the x component of that. We give that the symbol little u, u inertial. Same thing over here, u inertial. The right hand side, these are vector quantities. Over here, I just take the x component of those vector quantities, right? So I'm going to label this equation as equation 2x, indicating it's the Newton's second law applied in the x direction. Similarly, one can write down Newton's second law in the y or z direction, right? So what will change is instead of u, you will have v over here, v inertial, and instead of x over here, you would have y. And same way if you think about the z direction, right? So the things that will change are the ones that I highlighted in my circle, right? So instead of u, you would have v inertial for y direction and w inertial in the z direction. And then instead of x, y, x in the subscripts over here, you will have them replaced by y or z, as the case may be, right? And for a fixed control volume, where the relative velocity is the same as the inertial velocity, so in many cases, in many problems, this velocity v sub inertial and this velocity v rel may be the same in many problems, where typically when you have a fixed control volume, as we will see through examples, and as you saw through some examples when we did conservation of mass time kinds of problems. Then the advantages, the flow properties, and if you assume the flow properties are uniform across an exit or entrance sections of a control volume, that is, you make it one-dimensional, then you know all these integrals over here become simple products. And so you got the rate of change of momentum sitting on the left-hand side. This is the mass flow rate out, right, times the velocity with which it moves. So this is the outflow rate of momentum, and same thing, this is the mass flow rate coming in, and this is the velocity of the fluid measured with respect to my inertial frame coming in, equals sum of all the forces acting on the control volume, right? So in fact, this corresponds to equation 340 in chapter 3 in Frank White's 8th edition of the book, right? So this is kind of a more practical way of applying for real problems, as you will see. Equation 2 is sort of the most general form. Equation 2x is also useful when the situation is a little more complex, right? When you don't have necessarily one-dimensional flow, you kind of have to go back to this version. So in summary, we've got Newton's second law applied to a control volume. So our starting point was taking Newton's second law applied to a control mass, and then converting the control mass integral to a control volume integral through application of the Reynolds transport theorem, which is simply a bookkeeping statement. And then that's how we obtain the Newton's second law for a control volume.